Hello everyone! So today we're going to continue our discussion about phase diagrams by talking specifically about mixtures of liquids and gases and how we can use phase diagrams to tell us a lot about the composition of liquid gas mixtures, specifically as I start changing the temperature of the system. So in order to do this, we're going to pretty much pick up where we left off by examining our expression about how we can use the temperature dependence of the total pressure on for a mixture species, where our total pressure is going to depend upon the composition of the system, the net vapor pressure of each individual systems, and again, its response to temperature as dictated by the enthalpy of vaporization. So again, what we tend to find is that higher vapor pressures of individual components will tend to raise the total vapor pressure, as well as we're more likely to, at high temperatures, find a species that has the higher vapor pressure at that temperature. But in kind of practical uses, one of the best purposes to which we can put this equation is something rather simple, by setting the total pressure to 1 atm. Because as a reminder, this is the very definition of the boiling point, when the vapor pressure is equal to the external pressure. So assuming that we're not playing some finicky tricks with the external pressure, what this does is it lets us determine, for a given composition of the species, we can determine the temperature at which it boils. But also, kind of inversely, if I know the temperature, I can figure out the composition or the mixture that will boil at said temperature, if any given mixture will. So in practice, this is going to have a lot of real uses, in that mostly I know what temperature I need to go to raise a system to cause it to boil. And alternatively, I also know that, say, if I manage to boil something at a given temperature, what its composition is. And this relationship has a lot of uses in both analytical, but also in real industrial level separations. As it turns out, boiling something is a really good way to separate two species, especially when the vapor and the liquid have different compositions. However, one of the things to make note of is that this all assumed that we were working with an ideal system, because again, we started by making use of Raoult's law. So for a real solution, we then need to factor in the activity coefficients, which themselves are going to be temperature dependent. And this becomes a bit of a problem to solve for, again, real cases. So in practice, what we're going to really do is generate a curve of, again, the total of the relationship in between temperature and the mole fraction of both the liquid and the vapor from real empirical data. And generally what this is going to look like is that I'm going to have a certain temperature at which my more volatile component will tend to evaporate. And then as I increase the amount of the lower volatility component, again, according to Raoult's law, what I expect to see is boiling point depression. And indeed, we tend to see this. But similarly, as I say, have a system of composition A that now has a lower boiling point than I started with, well, we do run into the fact that my more volatile component, so the one with a lower boiling point, is going to tend to evaporate first. And as a consequence, what ends up happening is that the vapor is richer in the more volatile component. And this will generally be the case, that we're going to have some sort of line going from less volatile to more volatile component. The liquid will almost always be richer in the less volatile component, and the vapor will almost always be richer in the more volatile component. Again, in this case, A likes to evaporate, B doesn't. And we're going to tend to see a relationship that exhibits that. However, we also end up having these kind of fun points that say at this temperature 2, I've now generated this vapor that's richer in A, uh, with its own kind of composition. So as I maybe raise the temperature, what we're going to again increasingly see is a liquid that's going to be richer in B, a vapor that's richer in A, which we can then use to separate. But it's worth noting that the longer I let this system boil, as I'm removing A off of the system, the composition of my remaining liquid will become richer in B, which means that so will my vapor, and the whole thing will essentially all just slowly uh, vaporize together with a set composition. So this is again one of those things you kind of have to watch out for as we end up more or less where we start if I try and do this all together. So what we often do is make use of a couple of key tricks. So one of the first of which is trying to elevate the temperature past the boiling point. So I'm now in a point at which I say have a system with a composition of ZA, where ZA is the mole fraction of my mixture. And I go ahead and I reach my boiling point, say 1 at temperature 1, and then I increase it towards I'm now at temperature 3. At which point now what I'm going to have is the system will completely separate out. I'm going to evaporate out a small portion of the vapor into my B-rich phase, and I'm going to leave behind some liquid in my A-rich liquid phase. And again, this is a classic trick in, say, a lot of home cooking, where you have a component that may be poorly volatile, like most food items, and you try and evaporate out the more volatile component of water. And as long as you stay at a given temperature, you're going to reach some sort of equilibrium conditions. Now, as you might imagine, since this is a pretty decent separation technique, one of the things we're going to be most concerned about is what's going to be the amount of moles in our vapor phase, and what's going to be the amount of moles in our liquid phase. And so what we can do is make use of a couple of key tricks. So we can start with essentially the number of moles of A. Well, I know that all of the moles have to either end up in the liquid phase or in the vapor phase. So the number of moles of A in the liquid phase is going to be the same as the total number of moles in my mixture times the composition of the liquid phase. So ta-da, that's going to be one way of describing the number of moles in the liquid phase. Similarly, I can describe the number of moles in the vapor phase by noting the total number of moles in the vapor phase times what fraction of those are A. So again, this is another way of saying N of A in the liquid plus N of A in the vapor should be what I started with, because I can't just generate moles from nowhere. But we can also express this in a slightly different fashion. I know that the number of moles of A is going to be the same as the total number of moles times essentially the composition of A. All right, hopefully that makes sense. Well, what I can do is then treat it as the same thing of both of the total number of moles is going to be the same as the number of moles in the liquid plus the number of moles in the vapor, with essentially just carrying around the ZA, in this case, as a constant. So what we end up with is two different ways to calculate the total number of moles of A. One based on the composition of the mixture of the liquid and the vapor phase, and one based on the composition of which I started with. So what we can then do is, since these two expressions are going to be equal, I can try and take all of the terms which have the liquid phase and collect them together, and the same thing with the vapor phase. So treating the this first equation as being on my left. I'm going to subtract the number of moles of the vapor phase times the composition of my starting solution from both sides. And this leads me with an expression just in terms of the number of moles of vapor. And I can do the same thing for the liquid, subtracting out this first term onto the second side. Now, again, since this left-hand side is just in terms of the total number of moles of the vapor, that's more or less shared, so I can pull that out front. And the same thing with the liquid. And what we end up with is this relationship in between the number of moles and the difference in the compositions. So I have the number of moles of the liquid phase times how different the composition of the liquid is from the vapor, and from my starting material, and the same thing with the difference in the composition of the vapor from the starting material. Well, you'll notice that both of these denote two more or less lines on my phase diagram, and we call these the isopleth lines because they're the difference in between the isopleth and the phase of interest, whether it's the vapor phase or the liquid phase. So what we have is that the number of moles of the liquid is times its isopleth line is going to be the same as the number of moles of vapor times its isopleth line. So what this does is it gives me a way to describe the ratio of the moles in the vapor versus liquid phase as a metric of the length of these two actually rather easy to measure lines, which can be generated simply by knowing the shape of my phase diagram. And this general idea is called the lever rule. And one of the ideas is simply because it acts like a teeter-totter. If I have a central pivot point, the closer it is to, say, one side, the less weight I need on the less weight I need on the longer side to essentially balance out the point that's closer. The longer the lever, the less is going to be out on that line. So thus the lever rule. But also in practice, what this is going to tell us is something that's kind of logical. If I'm sitting here at temperature 1 at which boiling has just barely started, well, at this point, my isopleth line to the liquid is 0. So if I take my vapor, divide by 0, well, this is infinite, which means that the ratio of liquid to vapor is also infinite. So everything's in the liquid phase, which makes sense because if I'm just sitting at the boiling point, well, then barely anything has gone into the vapor. Alternatively, if I go to very high temperatures and I get to, say, temperature 4, at which point my vapor line is 0 because I'm at the vapor, well, then the ratio of the isopleths is 0, which means there's nothing in the liquid phase. So again, this kind of makes sense as we're walking up and down the isopleth. When I'm at the liquid line, everything's in the liquid. When I'm at the vapor, everything's in the vapor. When I'm in between, the closer I am to the liquid, the more liquid. The closer I am to the vapor, the more vapor. And you can use this as essentially a quick logical check. And if I'm halfway in between the two lines, well, that means I'm going to generate equal amounts of vapor as I will liquid. And hopefully this will make sense. And again, I do want to emphasize that this is going to be the total number of moles of liquid and vapor, not just the number of moles of A in the liquid and number of moles of A in the vapor. So again, this is going to be the total number of moles that ends up in their corresponding phases. But you may notice that this isn't exactly the most efficient way to, say, make pure mixtures, because what I'm going to generate is essentially a vapor and a liquid phase, which one may be richer in the phase that I want than the other, but they would hardly be what I'd call pure. In order to essentially generate pure species, what we can do is called fractional distillation. So the idea here is I'm going to be feeding in an input of a continuous stream of some given composition. And then I'm going to raise it to its boiling point, at which point I'm going to find some amount of a little bit of vapor is going to emerge off of the system. And then it's going to have composition this vapor is going to have a composition that's richer in the more volatile component, let's call it X, at which point I let it hit a solid plate with a lower temperature. Well, at this point it condenses out, and then I go ahead and at this lower temperature, there's going to be a little bit of vapor that will essentially evaporate off, and it's going to hit a second plate at an even lower temperature, at which point it condenses off, and then it goes ahead and it rises again, and then I go ahead and I take this vapor and I pull it out. And this vapor is going to have a composition that's going to be relatively high in the component I care about. In this case, X. Generally, it's going to be the more volatile component. And so I'll have a bunch of vapor in the more volatile component. I'll go ahead and cool it down, and then I'll get off the liquid distillate that we actually care about. And then I'll feed some of that liquid right back down to essentially keep the system in equilibrium. Similarly, as I'm feeding in my input, I'm going to let a little bit of that liquid fall down to a plate that it's a very high temp. And that's going to cause most of it to be in the vapor phase, but some of it's going to condense down in the liquid phase, where it's going to fall down below to a plate that it's an even higher temp, where it's going to essentially some of it's going to condense out, but most of it's going to evaporate. And the lower and lower down, the more I'm going to be rich in my less volatile component of, say, Y. And I'm going to pull off some of that liquid that just refuses to evaporate. And this is what's going to be called, in distillation terms, the bottoms. So I'm going to heat some of this back up and essentially allow it to flow in to keep the system essentially in equilibrium, so that the composition of each of these plates stays constant. And as long as the concentration, the amount in each of these plates stay constant, I don't have to worry about the temperatures going up or down, or essentially the system drying out or enriching. So I essentially going to keep myself stuck at each of these equilibrium points. And in practice, this is actually a very useful way of generating pure X and pure Y, as I'm going to pull off a hot liquid and a cold vapor, which may seem a little bit backwards, but again, the whole idea is you're pulling off something that evaporates easily and something that doesn't like to evaporate at all. And the greater the difference in the boiling points of your two liquids, the easier it is to make this separation. And this is the classic trick that is used in, say, well, most industrial separations, going anywhere from oil to alcohol. Except for, here's the thing that we run into, is this pesky problem that we only have a vapor phase diagram that looks this pretty if everything obeys Raoult's law. In other words, if it's an ideal solution, which means that they have to have very similar intermolecular forces. Well, that isn't exactly going to be the most common thing in things that have species that have different boiling points. So in practice, what we run into is this pesky problem that my Gibbs of excess is going to be not zero. So we're going to go ahead and separate these problems into two components. So the first is if our Gibbs of excess is less than zero. So as a reminder, if my Gibbs of excess is less than zero, what this means is that I have a negative enthalpy of mixing, which means that my mixture really wants to form. And I'd much rather be in the liquid phase than in the gas phase. So what sort of kind of consequences is this going to have for a mixture? Well, in practice, what it means is that my two components like to form a mixture. So in practice, this means that my boiling point is going to be lowered. And this generates what's called an azeotrope. So an azeotrope is this idea of a point at which I reach either a minimum or a maximum boiling point that isn't one of the two species. So one way to think about it is that this is going to be the composition that when I try and distill the system, it's going to naturally tend to move towards, because this is when my mixture is the happiest. It really likes hanging out with each other, and I maximize those kind of intermolecular forces at this composition. But in practice, this has some unfortunate consequences. Say if I go ahead and start at composition uh, I go ahead and I heat up the system to boiling, and then I try and perform a fractional distillation. So I pull off the more volatile mixture, which is going to be richer in B, condense it down, boil it, condense it, boil it, condense it, boil it, condense it. And what ends up happening is I very slowly approach this point B. But here's the point, I never get past it. So while it's possible for me to take this original composition of A1 and generate something that's pure A, I'm never going to generate an equal amount of pure B. So I'm only going to get to this kind of mixture. This is rather unfortunate if, say, I want something that's pure B, but it's also unfortunate if I want something that's pure A, because this means that I'm not able to get all of the A out. Some of that A is always going to be stuck in the mixture. So I'm never going to have a completely efficient purification going one way or the other. However, it turns out that a negative excess free energy isn't the only possible problem I may run into. It's also possible to run into a case that has a positive Gibbs of excess, which again means a positive excess enthalpy or a positive enthalpy of mixing. This is a fairly common case because this means my two solutions that I'm mixing don't like each other, which means that they're much more likely to boil than in the normal case. So in this case, what ends up happening is that if I start with a composition, mixture of composition of B or of A, I try and boil the system. Well, I'm going to say I'll generate some vapor. I then try and condense out the vapor, boil, condense, and what ends up happening is I generate a positive azeotrope. So a positive azeotrope is going to denote a system. Sorry, I mixed up my azeotropes. A negative free energy of mixing means that the two systems are going to want to hang out, which means that they're less likely to boil. So this generates a positive azeotrope, meaning that this is the point at which they're the most happy and won't want to separate. But in practice, this has a consequence that if I try and distill this mixture, I'm never going to generate pure A and pure B. Instead, I'm always going to get hung up on this middle point. So let's go ahead and think about what this would look like in a kind of a real case. If I have a system that's 50% by mass propanol. So by the way, this corresponds to a mole fraction about 0.77. So again, mostly propanol in water. And in this case, what ends up happening is that no matter how much I try and purify my propanol, I'm never going to get a system that's more pure than this 71.7%. So I'm never going to end up getting pure propanol. Instead, I'm always going to have this 70% mixture. And if you don't believe me, go to the drugstore and try and find some isopropanol. And you're going to find that it usually maxes out about 70%. Because at this point, it just gets too expensive to try and approach this azeotrope, because you're only approaching it slowly. Now, in truth, there may be other ways to get past an azeotrope, but they often involve kind of thinking tangentially. Because you can do similar distillation tricks, but instead of changing temperature, you might be able to change pressure. And again, there's going to be some relationship in between composition and pressure just as well, but you'll need a different phase diagram to walk that way. And there's also other methods of treating, which you can say use distillation to get yourself to 70%, and then using a drying agent to push your way across, at which point maybe you can push yourself far enough across that distillation might help again. But again, trying to use pure distillation, you're never going to try and be able to move past an azeotrope, which is one of the reasons why the highest proof of alcohol you're ever going to find tends to be about 190 proof, because there's a azeotrope for ethanol around 95%. You just can't quite get past it. You can indeed find 200 proof alcohol uh, in the lab supplies, but that's only because it's manufactured directly and not purified through distillation. So next time, we're going to focus a little bit more talking about liquid-liquid mixtures and kind of leave the vapor behind. Until then, take care.